Hello everyone, and welcome to another lecture of EE316 Communication Systems. Today's topic is about frequency and phase modulation. Frequency modulation is the process of varying the frequency of the carrier signal linearly with the message signal, while phase modulation is exactly the same, but the only difference is instead of varying the frequency, we will be varying the phase. So in the frequency modulation, the amplitude and the phase of the carrier signal remains constant, whereas the frequency of the carrier changes. This means that when the amplitude of the modulating message signal is increasing or decreases, the frequency is going to have different values. We're going to see this using the Simulink environment. So first we're going to construct our message signal of type sine wave. It is going to have an amplitude of 1 and a frequency, a message frequency of 10. Our sampling time is going to be 0.1 millisecond as we have taken in the previous lectures, and the samples per frame is 1. Now in Simulink there is what is known as the FM modulator passband. This is exactly the frequency modulation technique. So inside the FM modulator passband, we're going to choose the carrier frequency. We can choose anything to be higher than 20 Hertz, but the higher the better. So we're choosing 100 Hertz. Our initial phase is 0, so this means that there will be no phase difference or no phase shifting, and my frequency deviation is going to be 30 Hertz. After the modulation of any message signal, we have to do demodulation in order to get our original message signal back again. So in my FM demodulator passband, I have to choose the same parameters that I have chosen in the FM modulator. So I have chosen 100 as a carrier frequency and 30 as a frequency deviation. I will come to the FM demodulator passband and choose the same values. Now my carrier frequency is 100, my frequency deviation is 30. There is something called Hilbert transform filter order. What is this? This is going to help us to get back our original message signal after the modulation. The transform filter order must be an even number, and the higher it is, the better. The problem is of choosing a high value of this filter is that we are going to have more complexity, especially in terms of the mathematic calculations. But since Simulink does that by itself without our interference, so 200 can be suitable for us. It's okay to choose a high number since we are not dealing with any mathematic operations. The higher it is, the better the demodulated signal we receive is going to be. So after setting my message signal, my modulator, my demodulator, let's see the results obtained. Here, this is my frequency modulated signal in the frequency domain. As we can see here that the center is at 100 Hertz, which is our carrier frequency. Let's scoop in. Now the spikes, we can see that the spikes are we introduced at every message frequency obtained. So since our message frequency is 10 Hertz, this means that we are going to have a spike at 110, 120, 30, 40, and goes on like that. To the right and also to the left, we have a spike at 90, 80, 70, and goes on like that. So this is important. This is an important point to focus on. My carrier is my center, and my distance, the increasement of the spikes are obtained from the message signal frequency. Now let's look at it in the time domain. In the time domain, let's zoom in again. Now we can see that this is my message signal, this is my input. After that, it is going to be modulated in this form. We can see here that there is a frequency shifting between the lower part. As we can see here, this is the lower part. My amplitude is decreasing. I have a higher frequency range here. When my amplitude is increasing, in this point over here, we have a narrower sine wave. So this means that there is a change in my frequency compared with the lower value of the amplitude with the higher value of the amplitude. After that, after we use the filter, we obtain our message signal again, and this is my demodulated signal. This is my signal after using the filters. We can see that it have a similar shape compared with my message signal. So in conclusion, for frequency modulation, frequency modulation is based on frequency shifting, not phase but frequency. I have a message signal. After that, I'm going to do the modulator. After that, demodulator to obtain the message signal back again. In the frequency domain, the center is my carrier frequency, and the spikes are increased to the right and to the left with a value of my message frequency. Since my message frequency is 10, I have a spike at 110, 20, and like that. From the scope, we can see that for lower values, my sinusoidal have a frequency by itself, and then this frequency changes and becomes narrower when the amplitude of the message signal is increasing. So now let's take a look at phase modulation. One important note I would like to mention is in the spectrum analyzer here, don't forget to unclick the full frequency span and choose a span of 500 Hertz and a center frequency similar to my center frequency given in Simulink, which is 100. So unclick the full frequency span and make the span 500 Hertz and choose this to be exactly the same as your carrier frequency in order to obtain a similar result. Now let's move to the phase modulation. In phase modulation, it is exactly the same principle as frequency modulation, but the only difference is instead of changing the frequency, we will be changing the phase. So my message signal is going to have an amplitude of 1, my frequency is 10 again, but in here let's choose a cosine wave as my input instead of a sine wave. So a phase offset is introduced with the value of p over 2. My sampling time is 0.1 millisecond again, and it samples per frame is 1. My modulator passband carrier is 100, and my phase deviation in radians is phi over 2. So my phase deviation is b over 2 and my carrier frequency is 100 Hertz. This is in the modulator passband. In the demodulator passband, we have to give exactly the same parameters. So we're gonna have a carrier frequency again of 100, my phase deviation of b over 2, and that filter order of 200. After running this, let's see the results that we have obtained. This is my phase modulation in the frequency domain. Let's zoom in. As we can see, again the center is in 100 and the spikes are introduced in every 10 Hertz. Similar, exactly the same logic. Span again 500, carrier frequency the same. Unclick the full frequency span in order to obtain the same result. Now in my scope, this is my results. Let's zoom in to have a better view of it. In here we can see that this is my message signal. From where we can, from the increasing part of the message signal, we have a sinusoidal of saw, and then this sinusoidal changes its phase while the amplitude is changed from lower to up, from minus to positive, or as we can see from decreasing to increasing. The phase is changed here between these two parts as it becomes narrower. After taking the filter of that, we take the envelope, we obtain the demodulated signal. It have to be similar to the input signal, and it is as can be seen from here. There's only difference in ripple. This is due to the filter response, but in general it looks exactly the same as my modulated signal. So I obtained an output which is a demodulated signal, which is kind of similar to the message signal by using phase modulation. This brings us to the end of this lecture. I hope that it was beneficial for you. Thank you for your listening, and have a nice day.